Hi, I'm Will Bauer. I'm a middle school science teacher in Battleground, Washington. I was a OpenSciEd field test teacher for the middle school units. And I'm making this video to kind of share my experience with the 6.2 thermal energy unit for sixth grade. So this is the first one I field tested back in the fall of 2018. So in this video, we're going to mainly explore the anchoring phenomena and learn about kind of how you introduce the cold cup phenomena. In video 2, I'll discuss the storyline and we'll kind of see the big picture of the unit as a whole. Video 3, we'll talk about the norms and that OpenSciEd has and student discourse, how to encourage that in your classroom, and a couple other supporting resources that I found useful to get students talking when you're introducing an OpenSciEd unit and maybe changing how you've taught before. And then the last video, we'll talk about the assessments in this unit and how to implement this unit in your classroom, kind of go over some of the logistics and communities of support to help you get started. So let's begin here to talk about the anchoring phenomena. So let's start by first accessing the unit materials. So you go to OpenSciEd, you'll need to create an account. It's free, and click here to access instructional materials. And they have units in 6th, 7th, and 8th grade. And so I piloted all of these units, and they're the ones I did this last year. They're still getting kind of revised based off of the feedback from field test teachers like me. And then there's the 7th grade units, 8th grade units, and they also have some COVID-19 and health equity units that they made last year. So I made a video about the first unit in the 6th grade, light and matter. And this video series is going to be about the thermal energy units. Okay, so you click here to get to the overview, and you can go here to download the units. And there's a couple different options to download the units. You can copy the whole unit into your Google Drive or get like a preview and just copy what you need. And there's PDFs and print ready stuff. So that's how you find the materials. It's all free, open source. So before we kind of go into the anchoring phenomena, I want to use some of the PD materials from OpenSciEd to kind of talk about this anchoring phenomena storyline approach to these units. Okay, so the main thing I'll focus on here is talking about how the OpenSciEd curriculum is phenomena based. And so this unit will focus on the anchoring phenomena of the cold cup. So again, it's the second unit in the sequence. And these units are like meant to be done in this specific order. It's really logical, and a lot of the units, refer back to things that happened and that you learned in previous units. You can do them as a standalone unit, but I think they're more powerful and done in this sequence. So in the instructional model, you're following a storyline, and there's these routines that appear in each of the units. So this video is going to focus on the anchoring phenomena. In the second video, we'll talk kind of about the navigation routine and how you go from like one lesson to the next. We'll also kind of focus on the putting pieces together routine in my third video. and how to get students to kind of synthesize all the investigations they've done to revise their model and to have a more complete explanation of the phenomena that they than what they had at the first part of the unit. So that's the storyline approach, and we'll focus on anchoring phenomena in this video. And so the main elements of the anchoring phenomena are exploring the phenomena, and then we attempt to kind of make sense by building some initial models and doing some notice and wonderings. And then in the third part, we're going to identify a related phenomenon to the anchoring phenomena. So that step is important because we want to kind of broaden the focus of the unit to say, like, okay, well, we're learning about the cold cup, but the cold cup, like the knowledge that we gain by investigating the cold cup, can be applied to a lot of different scenarios related to conduction and insulation and so on. So thinking about kind of like the application of our knowledge is important when you're bringing up related phenomena. Is also an opportunity for students to bring in their outside knowledge and relate it to the phenomena you're introducing. And then in the last step, element 4, students are going to generate questions that they're going to want to investigate and come up with experiments to make more sense of the anchoring phenomena. So as you experience professional development in OpenSciEd, they have this language of switching hats. So there's the student hat, which is kind of thinking like a kid, and teacher hat, which is like thinking about how am I going to implement this in my classroom. So it's really important that, like, when you're starting to learn about these units, is to try to think about them from the perspective of a student, of a middle schooler. Like, have a particular student in mind and pretend that you're them, and think about what questions would they ask, what would they know, what would they be puzzled about, what would they draw in their initial model. And that will kind of help you kind of anticipate what questions might happen, where they might be confused, and you can switch back to teacher hat and think about, well, how would I guide them? What questions would I ask to get them to think about this more deeply? So it's important to think about this lesson from those two perspectives. Sometimes when we think only in teacher hat, we have this like expert blindness where we forget what it's like to be a novice learner, this new science content. Like, we know it so well and we learned it so long ago, we forget what that experience was like. So try to get out of your own head and think like a middle school student every once in a while when looking at these units for the first time. All right, so we're going to dive into the slides, the lesson slides that are in the teacher's guide for 6.2. And I'm going to kind of teach this like I would teach it with students in a very fast turbo speed way. And so be thinking, in your student hat perspective, and think about what questions that you would be coming up with. So I'm going to go through this fast because it's just me on video. So feel free to pause it at any time to jot down different things as I prompt you. Okay, so welcome class. So it's been really hot here in the Pacific Northwest, and it got up to like 114 degrees at my house. And one way I cooled off was by having some iced coffee. And you just can't drink hot coffee when it's 90 degrees at 8 o'clock, which it was at my house. So I had these two different cups. And I noticed that like the one cup that I used would claim that it would, keep my ice frozen and my cup cooler. So what do you think about that? Why do you think the drink in the regular cup warms up, and how could this fancy cup that has kind of two different layers of plastic, why would that fancy cup keep my drink from warming up? So you can pause the video and jot down your thoughts, like from a student's perspective. Why do you think the fancy cup keeps the drink from warming up? So we're going to investigate this claim that the advertisers have, the manufacturers have, of the fancy cup working better than the regular cup. So let's kind of jot down some ideas of how we could test this claim, and what evidence would we collect to prove or disprove the claim. Okay, so write down the claim in your notebook and write how you could test the claim and the evidence you'd want to collect. Okay, and then we'll share these out as a class. Okay, so you can pause the video and do that. All right, so we're going to, based off your ideas, we're going to take the temperature at different intervals, and here's a data table. So let me know if you think this is going to be a fair test. So we would do the test, and we're going to start to kind of like create a diagram of these two cups. So let's talk as a class, like what parts of the cup are important. What does each part do? What role does it play? And how do they work together to keep the drink cold? All right, so in your notebook, I want you to draw a model of how of your cup system. Okay, so draw one regular cup and one fancy cup. All right, and so the students would have data and they'd write conclusion kind of to start day 2. And so here's some sample data. So we found that the fancy cup was better at keeping the temperature colder for longer. Great. In this slide, they're going to talk about the norms. I'll talk more about that in video 2, but those are introduced more in unit 6.1 at the beginning of 6th grade. So students have now made looked at their data, they've made a model, a drawing of how they think it works. And now we're going to try to come up with a class model and a class drawing. And the purpose of this initial consensus model is to try to see where we agree, what parts of the system are important. Maybe we agree on what they do, and there might be parts where we disagree. Okay, this is just our initial consensus model, but we want to kind of bring identify and bring up in the discussion the parts where we disagree, because that might give us ideas for what questions to ask and what things to investigate, so we can kind of clear up the disagreements and find out what the truth is and have a deeper understanding of how this fancy cup works. So the next part, after we've come up with our consensus model, the students are going to share their related phenomena. So think about what other systems or objects keep temperature the same, maintain the same temperature without using electricity. Okay, so we're not going to kind of deal with anything with electricity, but think about things without electricity. That was one of your assignments for homework, but now we're going to create some drawings showing your explanation of how these things work. Some of the things might try to keep things hot. Some things might try to keep things cold. But one question I have is, do those things work the same? So I want you to make a diagram of the one item from our related phenomena poster and draw how you think it's working to keep something warm or cold. And now that students have made their model, they're going to go around and look at each other's, and we're going to jot down some similarities and differences of the models we have of the related phenomena. So now that we've looked at all these different items that keep things hot or keep things cold, and we have different explanations of them, I want you to kind of think about some questions that you might have. Okay? And then we're going to put those questions on our driving question board, one student at a time. And eventually we'll kind of group these questions into different subcategories. So now that we've kind of explored the initial cold cup, we've made a drawing about it, a diagram, a model. We've done an experiment to see that, yes, the fancy cup works better. We've also considered related phenomena that other students generated, where they found there's other things that keep things cold or keep things hot without using electricity. And we looked at some drawings and models that we created as a class. We've generated all these questions. So let's think about how we come up with answers. So we're going to jot down on a poster ideas for experiments, investigations, data that we need to help understand how this thing works. Why is the fancy cup working better than the cold cup? So that's kind of a wrap on or on the first lesson. And it might take like a couple class periods to go through this. I want to share a couple kind of examples of how I do this in my class. So now we're kind of out of student hat and thinking about how are you going to implement this with your students. So one thing that I used, especially this last year when I was teaching remotely for a large part of the year, was I started to use kind of technology to facilitate this. Instead of having posters all over my classroom, I used a couple of different apps to facilitate this, like anchoring phenomena routine. Okay, so this is a different unit, another one in the 6th grade about Mount Everest and earthquakes. And so this was, I had students post on Padlet a picture and an explanation of why they think the mountain is moving, how did the earthquake happen, and they write their explanation. So this is a really easy way to do a gallery walk, because it's all just on the screen and the kids can scroll around and look at what their classmates are thinking. So that might be a thing, that a strategy you use to use Padlet for your gallery walks or initial models. The only downside is that it's a paid app. There's a couple, you can use a couple Padlets for free, but now there's kind of a paywall behind it. But it was worth the investment for me last year. So the other thing I wanted that you can use that's free is Jamboard. So I pulled a few things from the teacher's guide that's available for you. It's always good to kind of read the teacher's guide to get an idea of what students might respond, and to look at sample initial consensus models, and so you can kind of know where the students should get in this first few days. And so here's a sample initial consensus model. So as a teacher, you've asked the students to all draw their own version of the fancy cup and the regular cup. And now you're trying to have them tell you how to draw what you should draw that they all agree on. And you can see here that they have some things that they've agreed on, but there's other parts where there's question marks, like, is it blocking the heat? Is it blocking the cold? What direction is the heat coming in and the cold going out? So it's good to have disagreement. That helps you transition to the driving question board and gives you reason for these investigations. So it's just trying to get, like, this routine is trying to get you to get these agreements and disagreements on paper and to revisit and revise later. And you're starting also to kind of work on some conventions, like and some labeling, so that when students compare their models, they're all kind of using the same arrows and stuff. Those are also kind of established in the first unit about light and matter, about how to kind of draw particles and how to draw light and reflection. And so that's going to be useful in this unit as well as you're doing more modeling. Another kind of strategy you can use is to use your initial consensus model as your driving question board. So after you've asked students to kind of play Pictionary with you and draw what their thinking is, then they can go up one at a time and put their questions on the driving question board on these little sticky notes. You can do it like physically, or you can create your own sticky note, like maybe it is the lid important, okay? And I can put my sticky note on the, I can start to group it, but because I've got this drawing, I've got this model to place it on. And so having your initial consensus model poster double as your driving question board, I think, is a really helpful strategy. It helps save space. If you're running 5 or 6 sections of the same OpenSciEd unit, like, you can run out of, each class has to have their own driving question board. You can run out of wall space. Or you can also, keep it digitally on a Jamboard or a Padlet. And then the other advantage is you can, by having your model, your consensus model, it makes it easier for students to kind of group their questions, and also seeing the physical, like, visual representation might help prompt them to come up with more questions. So I like to have them kind of together like this. And again, this is a sample I got from the teacher's guide. So I'll share a couple other examples that I used this last year. All right, so this was, our attempt at an initial consensus model for this Mount Everest unit. And, I drew this like while we were all on Zoom together, and the students were giving me ideas of what to draw and what to put on there. And we have it, represented in a couple different ways. And then later in the unit, we, added more things and revised our model, because we'd done some experiments. We investigated some of the questions that we came up with here. So that's one example of me using Jamboard. And then here's our driving question board and related phenomena, ideas to investigate. So you can have these kind of columns here, and students can add what their related phenomena was to earthquakes, what questions they had and what investigations they wanted to do. And then we could revisit this throughout the unit and kind of check off what we did. And it also kind of you can include like a picture of your initial consensus model as part of the background of your Padlet. All right, so that's kind of the end of this video. What I recommend that you do before watching the next video is to spend some time in Student Hat and create your own driving question board based off of questions you think middle school students would have, and generate a list of ideas for an investigation. So what you could do is use this initial consensus model slide here as a starting point, and make a copy of it for yourself. Here you go, just make a copy, and then you can add sticky notes of what questions you think middle school students would have about how the phenomena works. So work on that, and we'll revisit it in video 2 and see where in the storyline those questions are addressed. So that's it for video 1. Join me for video 2, which will go over the unit storyline, and we'll kind of look at the where the lessons go next after we've raised all these questions, exploring the anchoring phenomena.